A comet has just erupted near the sun, its brightness leaping overnight, its tail fanning wider than 5 full moons. The sky itself shifted in a matter of hours. What was once a faint traveler now blazes with sudden fury. Days later, the sun unleashed its mightiest flare in months, a massive wave of energy tearing outward, aimed directly toward the region of space where Comet R2 Swan is now racing toward Earth fast. On October 21st, Swan will sweep closer than ever before, crossing the ecliptic just as another interstellar object passes in near-perfect alignment. 2 cosmic visitors converging under the same sky. The timing is no accident. It feels like choreography written in fire and ice. And with solar storms set to slam into the comet's vast tail, the outcome is uncertain. Will the heavens erupt in a display unlike anything we've seen, or vanish into silence? The chain reaction is already in motion. What happens when starfire collides with a frozen wanderer? What story is told when a nucleus forged over centuries meets the unleashed force of a solar storm? These are not abstract questions. They are the drama unfolding above us right now. As of September 12, 2025, the world is watching. Swan, officially catalogued as C-2025, now simply called Swan, is rounding the sun at just half an astronomical unit, closer than Mars ever comes to Earth. At first, it looked routine, a faint, slow riser with a modest tail. But comets exist to defy routine. Only weeks after perihelion, its glow surged. The story is no longer about prediction. It is about transformation in real time, written across the night sky. And here on Lumora, we follow it step by step. September 26th brought the first signal that Swan had changed. Amateurs in Japan and Australia caught the surge, an almost full-magnitude leap, bright enough to push the comet into naked-eye territory under dark skies. By the end of that day, international forums lit up, buzzing with live photometry. Observers confirmed a brightness of 5.7, holding steady near 5.8 through September 28th. This was not noise in the data, it was real. Such outbursts point directly to the nucleus, the frozen heart of the comet, shaped by centuries of travel through deep space, now battered by relentless solar heat. Just weeks past perihelion, buried volatile pockets broke through the surface. The crust cracked, gases burst outward, carrying dust and ice into space. The coma swelled, the tail stretched wider. Every fresh observation became more than a number. It became a clue to the hidden machinery below. Thermal stress, sudden venting, local collapse, all are possible. Some watchers even reported jet-like features near the nucleus, faint but unmistakable, evidence of fractures or new vents tearing open. This was no longer a comet behaving by the standard playbook. Astronomers, both professional and amateur, now shifted their gaze. The numbers told the story. Swan had entered a new phase, its engine exposed, its future uncertain. The question was not only how bright it would grow, but whether this unleashed energy might fracture its very structure. The vast tail now unfurling behind it became both spectacle and warning. Stretching more than 2.5 degrees across the night sky, Swan's tail was no longer a faint thread. Imagine 5 full moons laid end to end. That was its reach. In suburban skies, binoculars revealed it as more than a point of light. It was a streak, a structure, a story written across the heavens. And for the first time, the world could trace its unfolding night after night, watching the changes not in centuries, but in hours. The scale of Swan's tail changed everything. For skywatchers, it was no longer a distant dot lost among constellations. It was a living structure you could trace with binoculars, a streak demanding attention even under city glow. Within that span, secrets revealed themselves. Knots of dust, shifting rays, and the faint electric blue of the ion tail, all sculpted by the solar wind. The comet's dual nature unfolded clearly. The dust tail, heavier and slower, clung close to Swan's orbit, forming a broad golden fan lit by the sun. But the ion tail, light and volatile, carried its own drama. Under the right solar conditions, it could ripple, bend, or even snap away entirely. This was no static picture. It was motion, transformation, fragile beauty under constant assault. Small telescopes began to pick out details, streamers twisting, kinks forming overnight, sudden bends that weren't there hours before. Observers tracking night to night found no comfort in stability. Change was the rule. A single evening revealed a new plume, a fading streamer, or a sudden brightening as the nucleus vented again. Across continents, amateurs stacked exposures, compared notes, and stitched together time-lapse sequences. Tail motion emerged not over days, but hours. Subtle color shifts were logged, icy blue for ions, golden white for dust. Chemistry, normally invisible, was revealed in shades across the sky. The comet's low southern position in September and October favored those watching from Australia, South Africa, and Argentina. They had front-row seats to the unfolding experiment in solar system physics. But northern observers were not left behind. As Swan climbed higher and the moon waned, binoculars from Europe and North America caught their own glimpses. This was more than spectacle. The sheer reach of Swan's tail set the stage for what was coming. When the sun sent its own shockwave into that same quadrant of space, the encounter would be written in this luminous veil. Every ripple, every disconnection, every sudden break in the tail would serve as evidence of forces no laboratory on Earth could replicate. September 28th, 0843 UTC, the quiet of the sun shattered. X-ray monitors spiked without warning as an M6.4 class flare erupted, the strongest in months. For most of September, solar activity had lulled, charts from NOAA's GOES satellites trending flat. But now the graphs lit up in real time, energy measured in millions of kilowatts surging outward. Within minutes, the Solar Dynamics Observatory in Soho confirmed the event. This was no small flicker. M-class flares are mid-tier, but an M6.4 earns the attention of every satellite operator, every forecaster. The source, active region 4232, a twisted sunspot cluster, was positioned in the very quadrant of the sun Swan was approaching. 30 minutes later, coronagraphs caught the blast expanding. A coronal mass ejection had launched, its speed between 800 and 1,000 kilometers per second, among the fastest eruptions of the year. Alarms rippled through operations rooms. Satellite teams braced for radiation spikes, but Earth was not the target. Instead, all eyes shifted to Swan. Just 2 days after its explosive outburst, the comet now stood directly in the path of the CME's broad front. For comet scientists, it was an alignment that defied odds. A fresh eruption in the nucleus, a sprawling ion tail, and a solar storm racing straight toward it. The numbers told the story. An M6.4 flare, a CME at nearly 900 kilometers per second, and a comet tail more than 2 degrees wide in the line of fire. Every instrument on Earth and in orbit was tasked to watch. This was not routine. It was rare, unpredictable, and alive with possibility. As forecasts updated, the key question sharpened. Would the CME's expanding front slice through the comet's ion tail, or sweep harmlessly past? Geometry mattered. Trajectory mattered. The sun had fired and Swan was in the corridor. For the first time in years, the drama of a comet tail disconnection might unfold where anyone with a small telescope could see it happen. Inside NOAA's Space Weather Prediction Center, the race began the moment the flare peaked. Analysts pulled up live feeds from Soho's LASCO coronagraph and Stereo A's heliospheric imagers, scanning frame by frame for the expanding arc of plasma. By 0845 UTC, the CME had fanned outward, its front traveling close to 900 kilometers per second, fast enough to cross the Earth-Sun distance in less than 2 days. Its angular width, measured at roughly 90 degrees, placed it among the broader ejections of the year. But the crucial detail wasn't its size, it was its aim. Model overlays showed the blast missing Earth by a safe margin. Relief, yes, but also a shift in focus. The CME's main lobe was projected to sweep directly into the sector of space where Comet Swan now blazed. This was where forecasting became geometry. Solar ejections don't travel in straight, perfect lines. They expand, twist, fragment, reshaped by the solar wind. To chart its course, scientists stitched together coronagraph images, mapping the leading edge against the positions of planets, spacecraft, and now, for the first time in years, a comet with a tail stretching over 2 degrees across the sky. Swan's coordinates placed it just inside Earth's orbit, slightly south of the ecliptic. That alignment brought it close to the CME's predicted corridor. The uncertainty remained. Without an Earth strike, plasma data would be sparse. Ground-based telescopes and orbital imagers became the best tools for tracking the encounter. Forecast centers worldwide flagged the event. Would the CME's broad front actually intersect Swan's tail or sweep harmlessly past? Best estimates place the arrival between 48 and 72 hours after launch. Long enough to build tension, short enough that the world would not need to wait long. For Earth, the risk was minimal, but for Swan, the consequences could be spectacular. Tail kinks, disconnections, rapid shifts in brightness, phenomena that usually unfolded in the dark isolation of space might now play out before thousands of backyard telescopes. The cosmic stage was set. The tools were ready. Data streams were open. Every eye turned toward the comet corridor. Magnetic fields would decide the outcome. A comet's ion tail is built from charged particles stripped from the nucleus and driven outward by the solar wind. These ions do not simply drift. They attach to magnetic field lines, forming invisible tethers that stretch millions of kilometers behind the comet. Under normal solar wind, those tethers remain stable, trailing like luminous threads across the void. But a coronal mass ejection carries more than plasma. It drags with it a tangled web of magnetic fields, each twisted into its own orientation. When those fields slam into a comet's ion tail, the result can be dramatic. If the CME's embedded magnetic field points southward, opposite to the usual orientation, conditions become ripe for magnetic reconnection. This is the cosmic equivalent of a circuit breaker snapping open. Field lines from the solar wind and from the comet's tail collide, break, and rejoin in new patterns. The stored energy is released in moments, severing entire sections of plasma. In practice, this means a comet's tail can simply snap off. Within minutes, a glowing fragment can drift away into space, while a new tail begins forming almost immediately behind it. The BZ component, the orientation of the CME's magnetic field, holds the key. Southward fields cut. Northward fields slip past, leaving only ripples. The process is fast, sometimes visible within hours. A comet's tail can kink sharply, fade suddenly, or detach in a luminous cloud moving on its own. For theorists, this is gold. For skywatchers, it is theater. No laboratory can replicate such scale. No simulation can fully capture it. Now Swan's ion tail, more than 2.5 degrees long, stood fully exposed. If the CME's magnetic field aligned just right, a disconnection event could play out in as little as 90 minutes. A drama usually hidden in deep space might unfold right before the world's cameras. Spectral signatures were the next signal to watch. If the CME struck Swan's tail, hydrogen and oxygen lines could shift by up to 50 kilometers per second as the plasma responded to the shock. Morphology would change just as quickly, faster than a feature-length film. A bright filament might snap free, drifting off on its own. A new tail could rise in its wake, luminous and raw. For scientists, this was a rare chance to study magnetic reconnection in real time. For amateurs, it was an invitation to participate in frontline science. Anyone with a camera, a modest telescope, even binoculars under clear skies could witness physics on scales impossible to replicate on Earth. Yet caution was critical. Not every ripple, not every dimming proved the comet had been hit. Geometry still held uncertainty. The CME's trajectory could veer. Its field orientation could spare Swan a direct strike. Experts urged vigilance over certainty. The task was simple but essential. Document, compare, report. Build a global record as the story unfolded. One truth remained. Change was inevitable. Swan was no longer a stable traveler. Every night carried the potential for anomalies. A sudden brightness surge. A kink where none existed hours before. A plume that faded into darkness. Each frame of each image could capture something no one had ever seen. And the timing made the stakes higher. October 21st, 2025 loomed ahead. Swan would pass just 0.25 astronomical units from Earth, only 39 million kilometers, 100 times the distance to the moon. For a comet, that was a close flyby, a once-in-a-generation event. The geometry was precise, almost uncanny. Its orbit crossed the ecliptic at a shallow angle, riding the very plane where the solar wind was most active. On that same date, interstellar visitor 3I Atlas would reach Superior Conjunction, opposite the Sun from Earth as Swan reached its closest point. Two cosmic travelers, separated by millions of kilometers, yet converging in the same corridor of space. The odds of such timing were almost impossible. And yet, here it was. October 21st was circled in red across every sky chart. Closest approach, new moon, the darkest skies of the month, conditions aligned with precision as though the cosmos itself had prepared a stage. From Buenos Aires to Perth, Swan rose early and lingered into pre-dawn hours, its tail sweeping across the southern horizon. Observers in Australia, South Africa, and Argentina reported breathtaking views, an arc stretching westward, shimmering against the dark. In northern latitudes, the show grew each night. After midnight, Swan climbed above tree lines, gaining altitude as October deepened. Star charts placed it near the border of Grus and Piscis Austrinus, easy to trace if you followed the line from Fomalhaut, the brightest star in the region. For binocular users, a standard 7 by 50 field of view captured the entire tail in one sweep. Small telescopes revealed finer detail, twists, knots, sudden bends. Even simple cameras on tripods could record the comet's streak with just a few seconds of exposure. And the parallax trick came alive. At 0.25 AU, Swan's apparent position shifted slightly depending on where you stood on Earth. Amateur crews coordinated across continents, logging rise times, sketching tails, and overlaying frames to track its evolution hour by hour. The checklist was simple: mark the position, sketch or photograph the tail, and watch for sudden kinks, brightenings, or fading. Each observation, no matter how modest, became part of a global tapestry. Every backyard astronomer added a pixel to humanity's shared record of Swan's journey. Scientists, meanwhile, watched for the CME's impact. Would magnetic reconnection shear off Swan's ion tail in a spectacular disconnection? Would plasma clouds drift away under the sun's relentless wind? Or would the comet hold steady, defying expectation once more? The answers remained unwritten. One certainty endured: this was a moment unlike any other. A comet in outburst, a solar storm in pursuit, an alignment with an interstellar visitor, and the Earth positioned perfectly to watch it all unfold. For those who lifted their gaze, Swan was no longer a line in orbital charts. It was a living drama, playing out in real time, written across the night sky. And here on Lumora, we bore witness together.